I think so. Just continue. So I'm happy to introduce Massimo Lauria. He will speak about space complexity of polynomial calculus.
Okay, thank you.
We all know that regarding such solving,
There are two competing views in, I would say, even in academy. There are people, mostly theorists, that treat SAT as the canonical hard problem in the field. While there are people in, I would say, in industry, but also in the part of academy that deals with industry often, that use SAT as a kind of
Your microphone isn't turned on.
Sorry? How should I? Top. Okay?
Yeah.
Okay.
The theory said that operating this microphone is very hard. The practitioner said it's very easy.
The point is that in people in applied context and industry, they use SAT as a commodity. They just reduce. They're happy if they can reduce the problem to SAT. Then we'll take a SAT solver, and they're happy with that. But this is, of course, this means that there's something more to say. In particular, the point is that SAT solvers can solve a lot of interesting problems efficiently, but there are a lot of domains in which we can get better, but still, even without hinting on a solution of the P versus NP problem, there are wide areas in which you can do better than current SAT solvers. And the essential motivation of this talk is to convince you that if you want to get better SAT solver, at least on a theoretical level, it's worth to study the next thing that we should do to improve SAT solving is to study memory requirements of algebraic SAT solvers and theorem provers. I want to convince you of this, and the main reason I believe this is that first of all, most of the SAT solvers nowadays are based on resolution, and algebraic reasoning usually has actually also been tested to be beneficial in the context of, at least in particular kind of application, for example, related to cryptography. This is why this is true, because why this is plausible that algebraic reasoning may be better. First, it gives you shorter proofs, shorter refutation. This is somehow provable. There are algebraic proof systems that are simple enough to be actually implemented. You don't want to define a proof system like even more powerful than extended Frege, because it would be useless in the context of SAT solving, of actual SAT solving. There are proof set algorithms for those proof systems, mostly based on Gröbner basis algorithm. And there are already good enough implementation to test and to put in the field. That has been put in the field. For example, polybory has been used in cryptographic applications so far. This is, nevertheless, this is not.
How well does it do?
Huh?
How well does it do?
I think that they can solve something which is not very large, but I think that most of the they're not in general. Their polybory is not good. It's not as good as modern SAT solvers, like you know, Lingelin, Minisat, and so on. But on particular application, it's more useful than, for example, general Gröbner basis algorithms, which are not tuned for cryptographic application, for example.
There have been talks for years about taking Gröbner bases and specializing them in Boolean rings and using them for SAT solving. But there's always the promise. It's very hard to deliver on the promise.
Yeah, and I want to discuss on this promise as well. My point is that that is not good enough, indeed. because such solvers are very optimal. They have a very carefully constructed data structures. They will manage clauses very efficiently. So no one would change the underlying paradigm and stop to be competitive in such competition for like 10 or 15 years. Would be crazy from their point of view. Also, the fact that you can have in some particular cases slightly shorter proof maybe is not very meaningful for them. Because one of the main issue in such solving nowadays is the issues of memory. Is the issues of memory usage and not proof length, or at least, of course, proof length is a problem, but for most practical purpose now, the main issue is space. And this is because when you run a such solver, most of the modern such solvers have closed learning inside, and they will, during the exploration of the search space, they will learn a lot of clauses, and the memory will fill up very quickly. And then when the memory fills up, you need to decide what you want to keep and what you want to delete, because you don't want to start to swap to the virtual memory. Would be ridiculously slow. And so it's very important to retain the important clauses and to discard the ones that are not important. But of course, it's not clear what clauses are important and what are not. So it's so if you want to say that algebraic proof systems are good for such solving, the question that we should really ask is, does algebraic reasoning helps in managing memory, managing space? And this can be formalized into questions. What are the memory requirements for an algebraic proof system, for an algebraic proof? And is there a better way in using algebra to trade space for time, maybe saving a little bit of memory without having too much longer runtime? Sorry for the slide full of technical stuff. But the point that in our result in this direction in particular are some lower bounds on the memory requirements of algebraic proof system, in particular variants of polynomial calculus. The first and only lower bounds in this framework was in 2002 by Aleknovich, Ben Sassoon, Rasborov, and Wiggerson, and they proved that pigeonhole principle, in particular, will require pigeonhole principle from n to n plus 1, from n plus 1 to n, would require order of n monomials simultaneously in memory. But the problem that this result was really required the fact that the initial formula have large clauses. Since we are mostly interested in narrow CNFs, we want to study narrow CNFs. In this work, we've been able to obtain similar results for variants of pigeonhole principle that can be expressed as narrow CNFs. In particular, in this talk, I will briefly sketch the proof of this result, which says that for this variant of pigeonhole principle, which can be described as 2 log n CNF, there is a quasi-linear lower bound on the number of monomials in memory. So for the rest of the talk, I will first define what algebraic proof systems are. In particular, the proof system polynomial calculus that I'm going to discuss, and I will give a model of space for this proof system. The models for space in proof complexity are not general like the space for the model of space complexity of Turing machine, because we still want to capture realistic algorithms. And then I will sketch the proof for the lower bound that I said before. So we all know what a proof system what a proof system is by now. It's we can think about as a non-deterministic Turing machine which decide if a formula is unsatisfiable. And these object proof systems are very important in computational complexity because I mean the motivating reason for which they has been defined was to study the question of whether NP is different from co-NP. The program because it's clear that if there is a proof system such that every unsatisfiable formula has a short refutation, then a co-NP would be equal to NP. I think some of us believe that this program is not going to be really effective, but that doesn't mean that studying proof system is useless because proof systems are also a nice theoretical model of SAT solvers. If you run a SAT solver and the SAT solver said that the formula is unsatisfiable, this is indeed a refutation. And more interestingly, most of deployed SAT solvers can be really modeled as proofs. The running of these SAT solvers can be modeled mostly in fragments of resolution proof system. Only lately, few solvers start to use algebraic idea, and then they're not anymore. They cannot be modeled anymore in the context of a resolution. Indeed, for example, Crypto Minisat was like I'm not sure was like a winner or a runner-up in SAT 2010, and it uses ideas, things that you cannot formalize in resolution, but you can formalize in fragments of polynomial calculus. So, what is this polynomial calculus proof system that I'm talking about? The idea is that you can encode the CNF formula as a set of polynomials in such a way that any satisfying assignment corresponds on a solution of this common roots of this set of polynomials. In order to do that, we encode the true and false as 0 and 1 respectively. A propositional variable will be encoded as a pair of two algebraic variables, and in order to ensure Boolean value for this variable, these polynomials are added to the set. In this way, it's easy to encode any clause of the initial CNF as a simple polynomial, actually a monomial. This is a slightly stronger variant of what is classically called polynomial calculus, but our lower bounds hold for this slightly stronger version. And I will only discuss.
Between PC and PCR?
Huh?
What's the difference between PC and PCR?
That they don't have this twin variable. They don't have this equation. So, for example, if you want to encode a large clause with a lot of negative literals, you will get an exponential, a polynomial exponential size to begin with. So you cannot even encode many formulas, for example. But in this talk, we are only focused on PCR. So when I say polynomial calculus, I will really refer to PCR. Then this is in inference system. So inference rule are that you can get linear combinations from polynomial that you already derived, and you can multiply a polynomial for one of the algebraic variables. When you define polynomial calculus, you really define it on a particular underlying field. So this linear combination, of course, are a combination of the field that you are considering. For most applications, usually people use GF2 because we deal with Boolean circuit, Boolean especially in cryptography. it's clear that since the inference roots preserve sumness, preserve common roots, if you deduce the polynomial 1, that means that the initial system of polynomials, they don't have a common root. So the formula which the system was encoding is unsatisfiable. And completeness follows because this system can easily simulate decision trees. Notice that this works also in fields that are not algebraically closed. So often Nostelens doesn't really apply completely. But since we are in the Boolean setting, we can always have completeness disregarding of the type of field we are considering. Several facts are known for this polynomial calculus proof system. There are exponential lower bounds on the length of proofs. There are relations between, it's an important complexity measure, the maximum degree appearing in a polynomial calculus refutation. And it has been discovered that there is a relation between size and degree. So you can prove lower bounds on the length by proving lower bounds on the degree. There are also papers dealing with the problem of searching proofs, automatizability of polynomial calculus. So at least on the theoretical level, at least regarding proof length, there is already quite a literature. So what's the model of space complexity in polynomial calculus? We may think a refutation in polynomial calculus as a sequence of memory configuration over time, and each configuration has a set of polynomials in it. An inference, a new configuration can be obtained by doing an inference step using two polynomials that are already in the memory. This is important. Those polynomials must be already in memory, and then you can deduce something from those polynomials. You can delete polynomials from memory, or you can either generate or download, depending on if your formula is uniform enough that you can generate the clauses, or if it's on external memory. You can download either a logical or non-logical axiom. In this model, we consider space as the number of monomial in a memory configuration. For example, this configuration has clearly 6 monomial. It's interesting to understand why we don't study, for example, the number of polynomials or the number of symbols. It turns out that you can always refute using a constant number of polynomials. The proof wouldn't be nice or small, but it will have at least a constant number of polynomials. And but if you want to count, for example, the number of systems, that I think that there are implementations for which the number of symbols would be a too expensive measure. You don't need to memorize monomials like spelling out all the variables for each monomials. So there are more efficient data structure that allows you not to, is not needed to count exactly every symbol appearing in the memory, every symbol appearing in this representation of the memory configuration. Very little is known for space in polynomial calculus. Only there was this lower bound for wide CNFs in this paper, Leknovich, Bensasson, Rasborov, and Vigerson. Quite recently, this is going to appear in stock 2012. Uin and Nordstrom, they proved a trade-off between length and space that applies to several proof systems. Actually, it applies to cutting planes, to polynomial calculus, to resolution. Even there are better results for resolution. And then there is the work that I'm presenting now that is going to appear in Complexity 2012, in which we prove the lower bounds for narrow CNFs. Closing, closing an open problem posed in this paper as well, because of course they asked if they can, if this result could be proved for narrow CNF. I will try to sketch the refutation, the lower bound, the space lower bound on the refutation of in polynomial calculus. So the formula that are that we are going to consider is this variant of pigeonhole principle. Let's assume that n is a power of 2. It's clear that there's no injective function from n plus 1 to the strings of length m, where m is the logarithm of n. This variant of pigeonhole principle may seem less natural, but it actually comes up often in context of bounded arithmetic, which I'm not really an expert, so we can move on. How to encode this formula is rather straightforward. For each two pigeons, we want to say that the two pigeons cannot be mapped to the same string, and so it's sufficient to if say the propositional variable fa1 encodes the first bit of the image of a, then this clause says that so essentially this clause says encodes exactly that a and b are not mapped on the same string s. I mean, if you want to an example to go, because to make things more clear, if you want to say that f1 and f3 are not mapped simultaneously is 1 1 0 1, we can encode it like that. So the theorem that I'm claiming is that this bit pigeonhole principle cannot be refuted in polynomial calculus if we want to have at most n over 8 monomials in memory. The idea of the proof is that, okay, we start with our refutation, sequence of memory configurations, and we are going to build an alternative sequence of special memory configuration. Those are not memory configuration in polynomial calculus, but they have a particular structure that I will say later. Those configuration, essentially each configuration implies the respective memory configuration. If the polynomial calculus refutation has a small space to begin with, then we can keep the special configuration to be small as well. So there is a kind of transfer of the space complexity of this refutation to the space, to the size of those special configurations. And when we move to the special configuration, then we are almost done, because the special configurations, if they are small, they are satisfiable. And this leads to a contradiction, because okay, we have a refutation, so the last memory configuration of polynomial calculus is contradictory. Since the refutation is small, we can have these small special configurations, but since those are small, they are all satisfiable. But if this is satisfiable, this cannot be satisfiable because there is an implication. So what is the structure of those special configurations? Those are special configuration can be represented as two CNFs, in which, with the particularity, strict two CNFs, so there's no unit clause. All clauses are exactly two literals, and no pigeon is mentioned twice in this configuration. So the first index of the variable is the pigeon, and no pigeon is mentioned twice in a configuration. The semantic of these special memory configurations are that a satisfying assignment will satisfy the configuration when it satisfies the two CNFs to begin with, and there's no collision occurring in the pigeons that are mentioned in the configuration. I mean, every assignment will specify a mapping. Will specify a mapping from the n plus 1 pigeon to the holds. No, it's for this configuration to be satisfied, it's sufficient that there's no collision on the pigeon appearing in the configuration. The reason this special configuration has been introduced is because if they are small, they are satisfiable. Things that is not true for polynomial calculus memory configuration. You can easily have a configuration with a single contradiction, with a single polynomial 1. But for this special configuration, a small size corresponds to satisfiability. So it's easier to control space complexity for this reason. It's, why this is satisfiable? See, there are at most n/2 pigeons appearing in a special configuration, in a small special configuration. So if we want to map every pigeon to a hole without having a collision, we can go pigeon by pigeon, and for each pigeon we have at least n/2 holes to choose from. So we can always map those pigeons. But the point that we also want to satisfy some of those literals along this process, during this process. But if we want to satisfy a literal, we have to fix one bit of the hole. And this will kill at most n/2 possible holes, possible free holes. So there will be still at least one free hole in which you can put the pigeon. So, and this can be done for all the clauses, and then we can satisfy the formula. So we started with this memory configuration that are small, and we want to obtain special configuration that are comparably small, and such that each special configuration implies the respective memory configuration. It's clear that the initial special configuration must be the empty one, because it will trivially implies the empty, because the initial configuration of the polynomial calculus refutation is the empty memory configuration. Then if we apply either an inference rule or a logical axiom, then we can use the previous special configuration, because those rules make only increase the size of the memory configuration, but they don't change the expressive power of the memory configuration. So Si will implies also mi plus 1. So we can use we can define Si plus 1 to be S1. This is more interesting. If we download an axiom and we put it in memory, this axiom will mention 2 pigeons. So we don't really care about what the axiom is saying, because as long as we name the axioms, we name those pigeons in the memory configuration, then all those axioms will be satisfied because of the semantic of the special configuration that says that no collision must be in the pigeon mentioned. So we just need to put inside the names of the pigeon. We don't even care about what literals we are adding. Of course, we just need to, we need to add each pigeon at most once. So we may need to add another dummy pigeon, which is not already in the special configuration. The most interesting case is the erasure step, which is quite complicated, and I don't have time to describe. But I will just say in a very superficial and very imprecise way that if monomial depends on 2 clauses in the special configuration, then the space complexity is preserved. If on average the monomials depends on more than 2 clauses, then it means that this dependence is very weak, so we can get rid of most of those clauses. So we can shrink the special configuration and obtain a small special configuration that will imply the memory configuration after the erasure. So just to recap, we started with a polynomial calculus refutation of size at most n/8 with polynomial space at most n/8. We we built a corresponding sequence of special 2 CNFs such that all such CNFs are small and so they are satisfiable. But this gives contradiction because the last memory configuration, it will imply that the last memory reconfiguration is satisfiable, which is a contradiction because in a refutation the last memory configuration would contain the end of the refutation, so will contain the contradiction. So, to conclude, we have. I mean, I'm arguing that polynomial calculus may be a candidate model for future SAT solvers. It appears to be that in some limited cases it appears to be the case because SAT solvers with algebraic reasoning are starting to be developed and deployed. But we need to study space issues because the memory issues in SAT solvers are very important. So if we want to get progress, that's the thing that we should study. And we have given very partial results on this regard because I mean those lower bounds are just the beginning of a line of investigation on this direction. So from the theoretical point of view, several open problems are open. Of course, technical results like we would like to improve to random 3CNF, for example, would be nice to say that random 3CNF requires large space to be refuted. Also, space lower bound for other viable proof system for SAT solvers, like cutting planes is a viable option for improving SAT solving. And so we want to study space for them. And also, if space really can be traded for time, also in these SAT solvers, and how good is this trade? From the more practical point of view, open problems are to improve PCR implementations. And but the most important thing is that those theoretical space lower bounds are very nice, but how they compare to the actual memory usage of SAT solver? This is an open question. There is some preliminary work on this direction, but I mean, are those space lower bound relevant to model memory usage in real application? So I conclude and I thank you for attention on behalf of my co-authors, and I thank you for the chance of talking in this workshop. Thank you very much.
Comments, questions?
So your lower bound is n over 8. What's your best upper bound? What do you have?
Oh, we can upper bound every polynomial calculus refutation, even in the simple proof system PC, with an upper bound which is the number of variables. I should go back. No, I think I.
So it's between n. The upper bound is n, and the lower bound is n over 8.
Okay, it depends. In this case, would be between n over 8 and log n, because here the number of variables increase. But for example, I mean, for the pigeonhole principle, for example, you can actually get in the simpler proof system PC, you can actually get an upper bound which matches the lower bound. So. I mean, this is in general, the upper bound is in general the number of variables. But for the pigeonhole principle, for example, you get a smaller lower bound, but you also get a smaller upper bound. So they match.
So, I mean, you try to relate it to practice, but it seems to me that these bounds for practice are actually very nice bounds. I mean, the problem with current SAT solver is memory really blows up.
Yes, that's why I say that we should investigate the relation between these, because those are, of course, non-deterministic proof systems. Those are the best strategy you can think. So a refutation in this proof system is somehow perfect in some sense. They know what the refutation knows what are the polynomials to keep in memory and not to keep. Jakob Nordstrom with several people that I don't remember, sorry, the name. They're trying to have actual data about the relation between space lower bounds in proof complexity and actual memory usage in reality. Because the point is that maybe if you need to remember a lot of clauses, and your heuristic is not perfect, it's just guessing, then if you need to retain a lot of clauses, there is more chance that you are deleting clauses that are, you are going to delete clauses that are important, even if you are caching a lot of them.
Perhaps there.
So you're referring to crypto minisat as an example. Crypto minisat uses some kind of PCR system in conjunction with a reputation-based proof system as the underlying proof system.
Sorry?
So crypto minisat uses this Boolean Gaussian elimination procedure for XOR clauses. It automatically discovers XOR clauses and eliminates them. So it's kind of a PCR system that's embedded inside a traditional reputation.
I had a slide on this.
The PCR is an extension of resolution also. It simulates resolution.
So yes, and so when I say that fragments of PCR, because of course crypto minisat essentially, assuming that you are dealing with polynomial calculus on GF2, then essentially PCR, crypto minisat together with clauses, it also manages linear forms in linear equations in GF2. Manipulates them, does the Gaussian elimination, and all those operations can be modeled in PCR. And also, I guess it's also sometimes it will transform the linear form in a bunch of clauses because you want to work also with you want the linear forms to interact with the clauses. So at some point you need to move from one language to the other. But everything can be simulated in PCR.
I think there are no further questions, so I think we have put away now.